Bienvenidos a la vigésima tercera edición del Coloquio Latinoamericano de Álgebra. Welcome to the 23rd edition of the Latin American Algebra Colloquium. We're extremely happy to see you here. I'm Jacob Mostovoy, the coordinator. If something goes wrong, it's my fault. So, well, these are somewhat uncertain times for science in general in Latin America, and not only in Latin America. So, but here we have a wonderful party. And, well, I'll give you information, some local information, but first, I'd like to pass the word to José Antonio de la Peña, who invited us here to this wonderful place. José Antonio de la Peña is a member of Colegio Nacional, which is, well, I don't know if you know, it's, I don't know whether I should say things about Colegio Nacional. Well, this is basically the organization, the body that unites the scientists, the writers, of artists of this country, and the events here are always special, and they are always organized by our best people. So, José Antonio, I mean.
Thank you.
So.
Buenos días. Well, the agreement with Jacob was that we will be very brief, and then we even say that perhaps we can take 10 or 15 minutes to start later. But I think it's fine. Okay, just continuing with some information perhaps about the Colegio Nacional. Let me say that the Colegio Nacional had the 75th anniversary this year. Okay, then let me say that during the activities of our meeting, there will be the celebration of the 60th birthday of Andrea. And then, well, I would like to thank Jacob for the organization of the meeting, and then Cinvestav for support given to the speakers, and even if Cinvestav is going through some difficult time, as many things in the country, many places in the country. Okay, what else? Well, then let me conclude just by thanking again Jacob for the organization of the meeting, and to all of you for your presence today, and then for the work during this week. And let me wish you the best of the meetings. Thank you.
Andrea Solotar, Universidad de Buenos Aires.
Hola, buenos días. Good morning, everyone. I'm here representing the scientific committee. So I want to thank all the members of the scientific committee of this meeting for their work, and also the organizers of the sessions who did a very, very difficult task and succeeded. And, well, as Jacob said, it's not the best time for science in Latin America, but we hope it will be better soon. So thank you for coming here. We know it's difficult sometimes. But...
María Ronco from Universidad de Talca.
Thank you. Well, welcome to everyone, and I want to thank in the name of the steering committee to the local committee, especially Professor Mostovoy and Professor de la Peña, who have worked fantastically. I mean, this place is really amazing. I didn't expect so a nice place. And also to the scientific committee, Andrea in particular, because we communicated and well, all the time asking her how things are going and so on and so on, and also the organizers of the sessions. And well, this the Colloquium of Algebra has been organizing during more than 20 years, I think, by Nicolás Andruskiewitsch, who took care of everything in a fantastic way. And 2 years ago, he decided we have to learn how to organize the colloquium. So we are more or less in charge without him, and I'm sure we are not doing as well as he did, but we are going on, and it's not a minor point, okay? Thank you very much.
Okay, so thank you. Now I'll say a few words about the logistic of the event. So first of all the information, all the schedules are online on the web page. I've updated the page yesterday, so we have almost all abstracts. As far as I understand, the information is practically complete. So the plenary session, the plenary talks are going to be here. And the afternoon sessions are going to be like 200 meters, well, maybe 500 meters away, across the pyramid in the Palacio de Autonomía. If you look at the map, please be careful looking at the map, because on the map there are basically two ways to get to Palacio de Autonomía, but one of them is closed. So in order to get there, you have to enter from the main square, from the Zócalo. You enter the Calle Moneda, and then you take First Street left. The street is called Primo Verdad. I have no idea who he was. Apparently, it was a person. Licenciado Primo Verdad. All right, so the building, well, it's not called Palacio for nothing. I mean, it's an imposing building with some cupola and all that. So it's just in front, it's just overlooking the Templo Mayor. No. I don't think so. I think it's an old building, but it's not so old. Yeah, well, whatever. I mean, you'll see the building. It has some. It really is a bit of a tourist attraction. Well, it's not very hard to find it. Right. So, what else? You'll notice some people selling things in the street. That's how things are done in the center of the city. It's not dangerous or anything, but still, I mean, if you want to walk without a direction, you should rather choose south or west. I mean, I guess I guess most of us are from Latin American countries. We know what things should look like. And, well, I mean, it's not dangerous if you go east. Actually, there is some interesting architecture. I do recommend it, but just don't go north. But let's say in some reasonable radius from here, everything is completely safe. What else? There's going to be coffee here and during the afternoon sessions. The afternoon sessions is going to be continuous. I mean, there are coffee breaks, but officially there is one coffee break, but if after the first hour of talks you really need some caffeine shot, it's going to be there. So it's going to be continuous. What else? There's going to be a lunch, a common lunch. Well, I think we have a reservation for some 40 people at the Osteria de Santo Domingo. It's going to be a serious lunch. Now, as I said, it's somewhat subsidized, but it's still going to cost about 200 pesos. It's worth it. So Osteria de Santo Domingo is not, I don't think it's on the map that I left at the hotels, but it's really close. It's one block up Donceles. Up means against the traffic. And then you turn right, and you are there, basically, I think. So it's really close. Now, there are going to be no tickets. We're not going to sell any tickets. We'll just, basically, your bill is going to be 100 pesos less than what it's supposed to be. What else? There are lots of tourist attractions around. What I recommend, something which is not a museum, it's the Secretaría de Educación Pública. It has wonderful murals. So, I mean, on the web page of the event, there is a sample, the mural by Diego Rivera, which is called Los Sabios. And, well, of course, I put it not to make fun of all of us, but I mean, somehow the situation is a bit making fun of all of us. And it's kind of a similar situation that we had about 100 years ago. So the murals are spectacular. You can enter. I mean, it's a functioning office, but you can say, voy a ver los murales, and they will let you in. Just remember that this is not a museum, this is an office, so it's open during the standard office hours.
And it's not far from here.
It's right on the, it's really close. Again, it's Plaza Santo Domingo. I mean, you can, well, okay, another thing is that, I mean, I apologize, but there will be some problems with the internet. So in Palacio de Autonomía is an old building. They have a problem with putting a landline, apparently. I have no idea. But for the case of emergencies, I have some SIMs I have some chips, Movistar chips, which are basically free. So if your telephone is compatible with Movistar, well, just ask me. And it has like 1.5 gigabytes of internet. So I don't really know what else I should say. I mean, I can keep talking, but I'd rather stop. So if you have any sort of questions, just ask me, and let's see if I know the answer. Thank you. So our first talk is in 11 minutes.
Pues estamos aquí, Mardonio Carballo y yo, para convidarlos al Colegio Nacional y también a este museo a un diálogo de experiencias compartidas. Los pueblos originarios, Mardonio, como tú sabes muy bien, consideran que los hombres de cierta edad, las mujeres de cierta edad, son personas de juicio, son personas cargadas de experiencia, y a ti se te ocurrió recoger esto para que dialoguen en distintas disciplinas personas que son decanos de su profesión con los que empiezan esa misma trayectoria de vida.
Sí, la gran maravilla, ¿no? La gran maravilla de tener también jóvenes expertos en temas diversos que de alguna forma importan pues en general al público, ¿no? A la vida, ¿no? Hablar de la vida a través del tiempo, hablar de la experiencia, hablar de la sapiencia también, ¿no? Que da la posibilidad de llegar a ciertas edades ejerciendo ciertas profesiones, ¿no?
Vamos a estar en diálogos los viernes hasta que acabe el año, prácticamente hasta el 13 de diciembre, y vamos a arrancar el próximo viernes 2 con un tema muy importante: identidad, pueblos, política, comunidades originarias de México. Vamos a seguir con el exilio español en México, un decano del exilio español hablando con una descendiente del exilio español. Seguiremos con un tema muy importante: salud, medicina, enfermedad, y así vamos a continuar con algunos de los temas más significativos de nuestro tiempo, contando con expertos ya muy probados, pero también con jóvenes que muy pronto serán expertos.
Sí, y qué maravilla que podamos tener un evento así. Esto es en colaboración con la Dirección General de Culturas Populares de la Secretaría de Cultura y el Colegio Nacional, ¿no, Juan?
Los viernes a las 7 de la noche, ahí en Donceles 104, Centro Histórico, los esperamos en el arranque del ciclo.
Diálogos a través del tiempo.
Pues estamos aquí, Mardonio Carballo y yo, para convidarlos al Colegio Nacional y también a este museo a un diálogo de experiencias compartidas. Los pueblos originarios, Mardonio, como tú sabes muy bien, consideran que los hombres de cierta edad, las mujeres de cierta edad, son personas de juicio, son personas cargadas de experiencia, y a ti se te ocurrió recoger esto para que dialoguen en distintas disciplinas personas que son decanos de su profesión con los que empiezan esa misma trayectoria de vida.
Sí, la gran maravilla, ¿no? La gran maravilla de tener también jóvenes expertos en temas diversos que de alguna forma importan pues en general al público, ¿no? A la vida, ¿no? Hablar de la vida a través del tiempo, hablar de la experiencia, hablar de la sapiencia también, ¿no? Que da la posibilidad de llegar a ciertas edades ejerciendo ciertas profesiones, ¿no?
Vamos a estar en diálogos los viernes hasta que acabe el año, prácticamente hasta el 13 de diciembre, y vamos a arrancar el próximo viernes 2 con un tema muy importante: identidad, pueblos, política, comunidades originarias de México. Vamos a seguir con el exilio español en México, un decano del exilio español hablando con una descendiente del exilio español. Seguiremos con un tema muy importante: salud, medicina, enfermedad, y así vamos a continuar con algunos de los temas más significativos de nuestro tiempo, contando con expertos ya muy probados, pero también con jóvenes que muy pronto serán expertos.
Sí, y qué maravilla que podamos tener un evento así. Esto es en colaboración con la Dirección General de Culturas Populares de la Secretaría de Cultura y el Colegio Nacional, ¿no, Juan?
Los viernes a las 7 de la noche, ahí en Donceles 104, Centro Histórico, los esperamos en el arranque del ciclo.
Juegüe, diálogos a través del tiempo.
Pues estamos aquí, Mardonio Carballo y yo, para convidarlos al Colegio Nacional y también a este museo a un diálogo de experiencias compartidas. Los pueblos originarios, Mardonio, como tú sabes muy bien, consideran que los hombres de cierta edad, las mujeres de cierta edad, son personas de juicio, son personas cargadas de experiencia, y a ti se te ocurrió recoger esto para que dialoguen en distintas disciplinas personas que son decanos de su profesión con los que empiezan esa misma trayectoria de vida.
Sí, la gran maravilla, ¿no? La gran maravilla de tener también jóvenes expertos en temas diversos que de alguna forma importan pues en general al público, ¿no? A la vida, ¿no? Hablar de la vida a través del tiempo, hablar de la experiencia, hablar de la sapiencia también, ¿no? Que da la posibilidad de llegar a ciertas edades ejerciendo ciertas profesiones, ¿no?
Vamos a estar en diálogos los viernes hasta que acabe el año, prácticamente hasta el 13 de diciembre, y vamos a arrancar el próximo viernes 2 con un tema muy importante: identidad, pueblos, política, comunidades originarias de México. Vamos a seguir con el exilio español en México, un decano del exilio español hablando con una descendiente del exilio español. Seguiremos con un tema muy importante: salud, medicina, enfermedad, y así vamos a continuar con algunos de los temas más significativos de nuestro tiempo, contando con expertos ya muy probados, pero también con jóvenes que muy pronto serán expertos.
Sí, y qué maravilla que podamos tener un evento así. Esto es en colaboración con la Dirección General de Culturas Populares de la Secretaría de Cultura y el Colegio Nacional, ¿no, Juan?
Los viernes a las 7 de la noche, ahí en Donceles 104, Centro Histórico, los esperamos en el arranque del ciclo.
Juegüe, diálogos a través del tiempo.
Pues estamos aquí, Mardonio Carballo y yo, para convidarlos al Colegio Nacional y también a este museo a un diálogo de experiencias compartidas. Los pueblos originarios, Mardonio, como tú sabes muy bien, consideran que los hombres de cierta edad, las mujeres de cierta edad, son personas de juicio, son personas cargadas de experiencia, y a ti se te ocurrió recoger esto para que dialoguen en distintas disciplinas personas que son decanos de su profesión con los que empiezan esa misma trayectoria de vida.
Sí, la gran maravilla, ¿no? La gran maravilla de tener también jóvenes expertos en temas diversos que de alguna forma importan pues en general al público, ¿no? A la vida, ¿no? Hablar de la vida a través del tiempo, hablar de la experiencia, hablar de la sapiencia también, ¿no? Que da la posibilidad de llegar a ciertas edades ejerciendo ciertas profesiones, ¿no?
Vamos a estar en diálogos los viernes hasta que acabe el año, prácticamente hasta el 13 de diciembre, y vamos a arrancar el próximo viernes 2 con un tema muy importante: identidad, pueblos, política, comunidades originarias de México. Vamos a seguir con el exilio español en México, un decano del exilio español hablando con una descendiente del exilio español. Seguiremos con un tema muy importante: salud.
Pleasure to be here in Mexico, the third time in the country, the second one in the city, so
significativos
I
de
guess
nuestro tiempo,
they will be grateful as the previous times. Let me start with the short words about something that happened to me. I was invited to give plenary talk the previous Coloquio Latinoamericano of Álgebra in Quito, but, well, my daughter was born at that moment, so I couldn't go. I would like to thank the organizer of the previous meeting for this invitation, and those of this meeting. This is a big opportunity to talk here, to give this plenary talk. A bit nervous because, well, this is the first talk of the meeting, but let's hope that everything is well. Okay, what is about the work? This is based in a joint work with Nicolás Andruskiewitsch from Córdoba too, and Milan Yakimov from Louisiana State University. If you see the title, you read Poisson, and you think maybe he's going to talk about geometry, but not in this talk. I will present the algebraic side of this work, where we discover all the Poisson structure, but from the algebraic side, by 3 reasons. First one, well, maybe I'm not the best expert in geometry to talk. Maybe you should talk with the other 2 co-authors, but I guess I can describe the things that I included in this topic. And the second one is that we are finishing this work. This is a work in progress. So exactly the last part, which is the real geometric side, we are discovering the last things. That's the second reason. But anyway, I discussed with my co-authors, and we decided that it is a good opportunity to present that all the results that we have here, until here. So I will present the dark side of this work. That's the thing. Okay, as this is a general algebra colloquium, let me say that I work with Hopf algebras, and all the work here will be around Hopf algebras. I'm not going to go deeply in this structure, but at least to present the definition, because I don't know if all of you know, maybe yes, but at least it is nice to fix the notation and all the things. Essentially, I will work over the complex numbers, and a Hopf algebra is an associative algebra with unit. Except that I say Lie algebra or Lie superalgebra, that they will appear later. When I talk about an algebra, it is an associative algebra with unit. And the Hopf algebra has also the dual structure, which is the structure of a coalgebra. So we have 2 algebra maps, which are the co-multiplication and the co-units, which one splits the terms in the tensor product of this algebra with itself, and the co-units which go to the scalars, the field that we have here. And we have an extra map, which is the antipode, which is an anti-algebra map. It means that it reverses the product. And I don't go to say nothing about the compatibility written here. I guess it is better. Why do we want Hopf algebras? In my opinion, the best thing is that with Hopf algebras we can provide tensor categories. What I mean by tensor categories, that we want representations of this algebra. We have an algebra, so we think in modules over these algebras. When I write small m, I mean finite dimensional modules. If you have two modules for these properties, well, you don't need finite dimensional, but for the remaining part of the talks, they will be finite dimensional modules. We can take two modules and to take the tensor product over the field of these two modules, and we have again a module over this algebra. How do we do this? With this map delta. As this is an algebra map, we can give a structure of module over the tensor product. With the epsilon, we have a structure of module over the field. So we have a one-dimensional module, the trivial one. And with the last map, the antipode, we have a structure of module over the dual of this module. This is the thing, essentially, that we have. If you think in which examples, if you don't see Hopf algebras previously, you can think which objects have the property about these things, to have the tensor product of two modules, the dual, and so on. The first example are groups. If you take representations over a group, you know that the tensor product of two groups is again a module. How do you do this? You put the group element to act in the first and in the second component. It means that you can take a commultiplication which is simple in this way. The commultiplication of each element of the group is G tensor G. And you take the linearization of this group, which is the group algebra. And this is the first example of a Hopf algebra. Then you can move to Lie theory, and you think, if I have a Lie algebra, and I want to consider the modules over this Lie algebra, okay, I can take the tensor product of two modules, and it is again a module. In which way? You act in the first component and add the action on the second component. This is encoded to have a commultiplication which is x tensor 1 plus 1 tensor x. But in this case, to move to associative algebras, I have to consider the enveloping algebra of this Lie algebra. And this is again a Hopf algebra. And just to finish the very brief introduction about Hopf algebras, let me recall two worlds of Hopf algebras where we essentially know the answer, and they are related with this classical representation theory, let me say in some way. If you look at this commultiplication, you can reverse the order, and you obtain the same commultiplication. And the same here. If I exchange the things, x tensor 1 becomes 1 tensor x, and 1 tensor x become x tensor 1. So essentially, I can reverse the order. What we have about algebras? One word that we study are commutative algebras. In this case, you say that the multiplication of the two elements or the reverse multiplication is the same. So essentially, what happens is that the multiplication is not affected by the usual twist of the tensor elements. Dually, we can talk about co-commutative. This is what I expressed for the previous two examples. What you can do, you can exchange the order of the tensor product, and you obtain the same co-multiplication. And because of the previous slide, we know that the group algebra and the enveloping algebra are examples of co-commutative Hopf algebras. Okay. Now the question is if we know all the things about these two words, and yes. Because of the work of many people, for the first description, essentially it is the result of a Cartier, which relates commutative Hopf algebras with algebras of functions of algebraic groups. This is what we have for the commutative world. And if we go to the co-commutative world, then we need some semi-direct product of the previous two things that I expressed previously. We need a group, and we need a Lie algebra. How to recover this group and the Lie algebra? Essentially, the group is made by all the elements whose coproduct is in the same shape as the group that I presented previously. The coproduct of an element is the element, tensor product, the same element. And for the Lie algebra, all the elements whose coproduct is in the same way as the Lie algebra. what are called primitive elements. So essentially, we can recover these two elements, and we know that we have an action of the group over the Lie algebra, and with this, over the complex number, we know all the co-commutative examples. Okay. Now the question is, what happens if we move outside this world? We want to obtain non-commutative, non-concommutative algebras. And this is related with the quantization process of these enveloping algebras, essentially. There were some examples of non-commutative, non-concommutative algebras previous to 1986. But in this year, essentially, we can say that the theory exploded because of the presentation of the quantized enveloping algebras by Drinfeld and Jimbo. What are these objects? First, I should recall what we have about the enveloping algebra of a finite-dimensional semi-simple Lie algebra. I recall that if we have a finite-dimensional Lie algebra, then we have attached a finite Cartan matrix of integers. And how do we describe the structure of this algebra? The first thing is that this algebra has triangular decomposition in a positive, a zero, and a negative part. The zero part is the Cartan subalgebra, which is an abelian Lie algebra. In that case, it is trivial, but the action of this Cartan Lie algebra, the commutative part, controls the theory, the representation theory of the whole element. And, well, we can fix a basis of this Cartan subalgebra, and then if we fix the Borel subalgebra, we have the positive part, which is a subalgebra generated by EIs. It is not of dimension theta, but the number of generators is the same, and the same for the negative part, and these are called Fi, usually Fi. What about the relations in the Lie algebras, which will become the relations for the enveloping algebra? Essentially, this Cartan matrix describes the action of the Cartan subalgebra over the positive part. This bracket is the usual bracket, Hi Ej minus Ej Hi in the enveloping algebra. And we say that this is a multiple of Ej, given by this Cartan matrix. For the Fj, we have minus this action. And then we have a compatibility between the positive and the negative part. Ei and Fj commute, except when the index is the same, in which case we obtain the corresponding element in the Cartan subalgebra. And then the question is how to generate the positive and the negative part. And the ideal of relations is given by what are called cell relations. Here, adjoint means to take this bracket. Adjoint of Ei is the bracket of Ei against each element. So we have to iterate this adjoint action. I recall that the entries outside the diagonal are non-positive, so 1 minus Aij is at least 1. It's an integer which is at least 1. And this Cartan matrix, because of the representations of SL2, we can derive in this way. We can see that we have these relations, but they are enough to generate the ideas in the positive and the negative part. How this is translated to the enveloping algebra? Essentially, we have a decomposition of the enveloping algebra as the tensor product of the enveloping algebra of the positive part, the zero part, and the negative part, where these ones are just polynomials in the Hi. And this equality means essentially that we have an isomorphism given by the multiplication. Essentially, every element can be written in a unique way as a sum of product, first the positive, then the zero, and then the negative part, but we can reverse the order too. And because of the PBW basis theorem, we know that if we have a basis of each part, then we have a basis given by the multiplication, because I say that this equality is essentially an isomorphism given by the multiplication. So I can fix a a basis of the positive part, in some sense the dual basis of the negative part, and we can attach this to every element of the positive roots. We know that we have an element for each positive root because essentially for the semi-simple Hofalgebra we have only one, the eigenspaces are one-dimensional. So we can attach only one element. And PBW basis means that if we fix an order, then a basis is given by all the ordered products to any power. What is the quantized enveloping algebra? In this case, we are going to construct a Hofalgebra over the fields C of Q for an indeterminate Q. And we fix essentially something in degree 0, something positive, and something negative. Now we have an action in the sense that these Ki are invertible. So we can think that how they Q commute with the E chase. And I forget here a DI, which is the diagonal matrix, making the Cartan matrix symmetric, but it doesn't matter so much in this case. You can think the simplest case. And we change the relations in this way. We don't say that they, well, we have some action. It's not, this is the formation of the previous one. But here you can recognize the same way to, or a similar way to relate the positive and the negative part. We say that EIFJ commute except when the index is equal, and in this case we take Ki minus Ki inverse, or you can take some multiples of this. Essentially, in many cases, you can divide this by some non-zero scalar, but this is okay. And this describes the action of the zero part against the positive and the negative part, and the relation between the positive and the negative part. What are the relations inside the positive and inside the negative part? We have some deformed cell relations. Here I take the braided adjoint action. I'm not going to explain in detail, but it is some deformation of the previous adjoint action. We don't take EI, EJ minus EJEI. If not, we put some scalars in the middle. This is essentially what it means. But you can see that, in some sense, this is some deformed version of the previous one. What is good about this algebra is that we keep the triangular decomposition. I mean, we can take the subalgebra generated by the EIs, the FJ, and the KA, and the multiplication induces an isomorphism. And then we concentrate to find a basis of this guy, a basis of this guy, which in some sense it is one is dual of the other. And we find that, again, the root system plays a very important role to describe this algebra. Essentially, what happens with this algebra, if you look at these relations, we can put a degree alpha j, where alpha j is the canonical element, just a 1 in the position j and 0 everywhere. We put degree 0 for the ki's and minus alpha j for the fj, and we can see that this is a set to the theta graded object, because all the relations are homogeneous. And we can find, sorry, this should be a big E beta, and here big F, capital F beta. We can find elements where the degree is given in some sense for the root, and we can find a PBW basis in the same way. The small difference that here we should admit positive and negative powers, because this Ki has an inverse. Just this is the unique difference. Okay, this is a Hofalgebra. Yes, you can put the Ki's with the multiplication as in the group algebra. They are called group-like elements. But to do this, to make non-commutative, we put some co-multiplication on the EI's and the FI's, which is not symmetric. This is what is called skew primitive elements, because they look like a primitive element, but they are not really a primitive element. And you can check that with these co-multiplications, all the previous relations are compatible, and you can induce a co-multiplication on this quotient. And because of the previous relations, for example, this one, you can see that this is not a commutative algebra, and because of this coproduct, this is non-commutative. And I introduced these algebras because they are the starting point for our work. Indeed, they are called in some cases quantum groups. And the title is about large quantum groups. What I mean is that we found a family which is bigger than these quantum groups where we can do some things as I will present in the next slide. As this is an algebra, I recall that this is an algebra over C of Q. If you have an algebra here, what you can do is to evaluate this variable Q in some element of C, and then you obtain a C algebra. You extend the scalars. This is what you do. This is what I mean by evaluation. And the thing is, what is the behavior of this algebra depending on the properties of this value that we take? And you can see that if this value is not a root of unity, the representation theory is essentially the same as for U of G. So we have a deformation, but the representation theory is the same. The critical point is to take a root of unity. And this was studied in the 90s by the Concini-Cat Procesi in a series of papers, some by the 3 authors, some of them by 2 of them. I guess you have the 3 possible combinations. So that's the reason why I prefer to say the 3 names, because some of the things are of papers of 2 of them. And we want to know what happens when we take a root of unity. So we fix psi, a root of unity of order L. Nice, I means that we have some restrictions, but they are small, and I don't want to enter in detail of these things. And then we evaluate Q in this root of unity to have a C algebra, which will be a C-Hoff algebra. And, well, again, it will be generated by these 3 elements. And essentially, the relations are the same. Essentially, what means the same is each time that you have a power of Q, you can take psi to the same power. Because you can write the relations. They are written in the previous part in a compact way, but you can extend this to write as a linear combination of monomials in these letters, and then the scalars are some polynomials in C, in the variable Q, so you can evaluate. And you keep the triangular decomposition, and you keep the PBW basis. Everything is fine. And this happens because of the way in which we choose these things. So the question is what is new about this evaluation? The big part is that if you remember the relations, here you have, if we evaluate in psi, then you have powers of psi. And this is a root of unity. So this may become 1. And this is what happens. If you take E beta to the L, F beta to the L, and Ki to the L, these elements are central in this algebra. So we have a very big central algebra. And this is the key point to study the representation theory of this guy, this algebra. Okay, what you can prove is that the basis is the one that you expect, just to take the previous power, which are multiples of L. So then we can quotient by this central algebra to obtain a new algebra. And there are 2 main ingredients about this quotient. First one, the big algebra becomes a finite module over this one. Why? Because you can find the basis given by restricted powers. As this is a central subalgebra, you can take a power and to divide the remainder by the division of L, and then to keep powers of L. This is a way to prove that it is a finite free module. This is quite strong. The second thing is that this is a Hopf subalgebra. So you quotient by a central Hopf subalgebra. The quotient will become a finite dimensional Hopf algebra. And this will be very good. At the same time, as this guy is a central Hopf algebra, in particular it is a commutative algebra, commutative Hopf algebra. So it is the algebra of functions of an algebraic group. And this is very nice. Some other features about these things. Well, the kernel that you obtain here is something which is known as the Frobenius-Lustig kernel or small quantum groups. And they are finite dimensional Hopf algebras. So in some sense, this is a way to construct finite dimensional Hopf algebras. Please don't confuse this construction with the construction by Lustig, where the small quantum group is inside some kind of quantum group, not a quotient. This is some difference. The second thing that you can find is that because of some things that I will describe later, we have a Poisson algebra. It means that this commutative algebra has a bracket which makes this algebra a Lie algebra in such a way that we have the Leibniz rule. And this is quite important for the geometric study of these things. The question is how to obtain this Lie algebra bracket. And we will see that this becomes because of this evaluation that we have in the previous slide. And moreover, this bracket is compatible with the coproduct, which makes it is written, well, we can define that this is a Poisson algebraic group. Poisson algebraic group means that the coproduct on the algebra function is compatible with this bracket. It means that the counit annihilates the image of this bracket. It is compatible with the antipode and also with the comultiplication. Where here we have the bracket into the coproduct has the image in the tensor product of the algebra with itself, and the bracket here is induced by the previous bracket component by component. This is essentially what you have. Okay, so we have some Poisson structure on this algebraic group. And the thing is that these three authors, the Concini, Katz, and Procesi, studied the representation theory of this guy using the structure of this guy. They used the geometry to describe the representation theory. Why? Because essentially, if you take what was the main point is to understand the irreducible modules of this algebra. If you have an irreducible module, because of your lemma, you have a character of the central subalgebra. So you can think this map going from the irreducible modules to the characters of this central subalgebra. And you look at the fibers. And they understand that the behavior of these irreducible modules over the algebra U are controlled by the fibers or the geometry of this algebraic group. Later, because of this work, Brown and Gordon, not only this work, some other works in some other contexts, they understand that, okay, all this talk and all these works, all these things belong to non-commutative algebra. The question is how to study the representation theory when you have a non-commutative algebras. It is quite hard. But maybe you have some way, if you have a non-commutative algebra with a big central algebra, and you try to make the same job. Try to understand the representations of this central algebra and try to see how this controls the big algebra. This is essentially the key point. And one of the key points is that you have a finite module over this central algebra. This is a way in which you control the representation theory. As I said, we have a map from the irreducible modules of the algebra to the characters, so maximal ideas of this central algebra. This will be the important ingredient here. And we fix any finitely generated algebra, we need this condition, a central subalgebra, such that we have a finite module. A is a finite module over this central subalgebra set. Brown and Gordon introduced what is called the Poisson set order. And This is a family of derivations. You have a map from the central subalgebra to the derivation of the big algebra A in such a way that Z is stable by these derivations. And if you take a bracket induced by this derivation in this way, the bracket between Z and Z prime is this Z of Z prime, then this gives a structure of Poisson algebra to Z. Okay, this is the definition, but we will see how to obtain a kind of these Poisson orders. Essentially, the idea is that they found that this is the case not only for the quantized enveloping algebra as a root of unity. It is the case for many other families in the context given upstairs. Okay, one important remark is that in some sense it is better to construct Poisson orders over the center of the algebra. But for many reasons, for example, for the small quantum groups, it is not good to take the center. Why? For example, what happens for the quantum groups? The center is not a Hopf subalgebra. So we don't have the algebra functions of an algebraic group. Sometimes it is better to take some subalgebra of the center in order to keep some other structures. In our context, the idea is that we will take a central subalgebra, which is a Hopf algebra, in order to have an algebraic group. This will be the main point. Okay. Some consequence, if you have Poisson orders, is that you can introduce some equivalence relations between the maximal ideals, which is given by to have the same Poisson core. The Poisson core is the biggest Poisson ideal contained, sorry, here I have a mistake, contained in M or in N. You can see that the sum of two Poisson ideals is a Poisson ideal, so you can take the biggest one. The sum of Poisson ideals is a Poisson ideal, so you can take the biggest one inside some ideal. You have an equivalence class, and then you have what is called the symplectic core of an element, which is the equivalence class of this guy. And for those who know about Poisson geometry, this is close to symplectic leaves. Indeed, I prefer to write the result in this way, but they relate the symplectic cores with the symplectic leaves in some cases, and they obtain that they are essentially the same. And the idea is that these symplectic cores are locally closed. We have here a topology, so we can think that they are the intersection of a closed and an open subspaces, and they give what is called well, this is a kind of stratification of Z. I'm not going to enter in detail, but this is what happens with these symplectic cores. Essentially, what happens is that if you take the closure of these elements, it is a union of symplectic cores. And this is quite important to study the geometry. But for our purposes, what is so important is that if two elements are related by this equivalence class, then the quotient of the ideas generated by these maximal ideas of the central algebra give the same algebra. This is a way to say that the fibers are the same when you take two maximal ideas in the same symplectic core. Because if these algebras are the same, then the irreducible representations attached to these quotients, AX and AY, are the same. So this is the first theorem where we see that the geometry controls the behavior of the representation theory of the biggest algebra. It is quite strong. If they belong to the same equivalence class, then the representation theory is the same for these quotients. And we can, as I said, we can study the representation of the biggest object in parts related with the representation theory of the central algebra. Okay. As I said, this applies for the particular case of quantized enveloping algebras, where we evaluate this in a root of unity. Why? This is a procedure which was included in the Konchini-Kaplan papers. Essentially, the idea is to take a big commutative algebra. In our case, it will be C of Q. to take an algebra over this big commutative algebra, which will be the UQ of G, and then to think to divide by some not zero divisor in this A hat. In our case, Q minus psi, which is the way to say that we evaluate Q in this root of unity psi. Well, we can take an element of the center of the quotient, A, and then to give a structure coming from something upstairs. Essentially, we take the commutator in the big algebra A hat, and we take the quotient, the image in some sense, we remove a copy of H, and then we take this image, where these are two pre-images of these elements. You can prove that this is a well-defined map because here we pick up some pre-image of Z and I. And moreover, you can prove that this is a map from Z to the derivations of A. And even more, what you have is that you have a Poisson order over the, in this way you define a Poisson order over the center. Here it should say Z of A. So in principle, what we have is a Poisson order on the center of this algebra. But recall that we don't want the center. We want something smaller. For the derivation, it is fine. You can restrict. But remember that you need that this set of this small subalgebra is inside the small subalgebra. So this is what you can check. And this was essentially included, not in this procedure because Poisson orders were not defined for the papers of De Concini, Katz, and Procesi, but this was written in this way. That's the reason why I say that Brown and Gordon essentially extended this structure. They abstract the definitions included in the papers by the Concini, Katz, Procesi. They say this explicitly. Okay, now what I do. My work is about classifications of Hopf algebras. Indeed, the first part of my research was concentrated in finite dimensional Hopf algebras. If I want to study finite dimensional Hopf algebras, then in particular I studied the small quantum groups. When you want to classify these finite dimensional Hopf algebras, you understand that this family that I studied, the pointed Hopf algebras, have a group in the middle as the small quantum groups, because the zero part is a group. And you can take some graded object attached to this some graded algebra, and a subalgebra of this graded algebra is what is called a Nicolás algebra, I will introduce now. And essentially, the combinatorics of the Hopf algebra, of course, has a relation with the group involved here, but a big part of the combinatorics of this Hopf algebra is captured by this, what is called the Nicolás algebra. I will, as I said here, I will go big up. The positive part of the small quantum groups are examples of Nicolás algebra. So what I'm going to study are generalizations of the positive part of small quantum groups. Just a few words about how to construct these Nicolás algebras. What we know are braided vector spaces. And this definition is quite simple. We need a vector space and an automorphism of the tensor product of B with itself, which satisfies what is called the braid equation that I wrote there. And essentially, because of this equality, what we have is some way to exchange things. This is what we have. And the Nicolás algebra is some universal quotient of the tensor algebra. What you can do is to define, quantum symmetrizers, because there is one for each n bigger or equal than 2. What you can do is, in degree 2 or more, you quotient the tensor algebra by the kernel of some linear map, which is called the quantum symmetrizer. And in some sense, essentially, there is a way to define this. If you use the Matsumoto section, then you have the symmetric group, and you go up to the braid group, and define an operator in the same way as you lift the things. And you add, so you have a linear map, and you quotient by this guy. But in words, I can tell you a different definition. Essentially, what happens is that this Nicolás algebra is not exactly a Hopf algebra, but it is a braided Hopf algebra. This braiding on B induces a braiding on the tensor algebra. So you have some kind of braided Hopf algebra, the tensor algebra. And you quotient by the maximal ideal, which keeps the Hopf algebra, the braided Hopf algebra structure. This is what you do. You quotient in degree 2 or more. So this is a graded algebra. At least you can keep this thing. This is a graded algebra. Examples of solutions of the braid equation. Okay, one example is the usual flip. But you can add a small detail to become a diagonal braiding. You fix a matrix of non-zero scalars, and xi is the flip, except that you modify by qij. This is what you do. And you can check that this is an easy solution of the braid equation. Then you have the corresponding Nicolás algebra. Although the braiding is simple, the Nicolás algebra is quite hard to be described. In particular, as I said, we can recover the positive part of the small quantum groups. Okay. Because of the relation with the Hopf algebra classification, Heckenberger found the list of all matrices Q such that the corresponding Nicolás algebra is finite dimensional. And I was able to find a set of generators of the ideal. I remember that I said that the Nicolás algebra is a quotient of the tensor algebra. So what you want is to find generators of the ideal of relations. What about these relations? Well, we have the same kind of quantum cell relations as in the previous case. If you look at the quotient defining the small quantum groups, you have to quotient by x alpha to some power. This is what we call powers of root vectors, and you have the same kind of relations. But then you need more relations, which are relations in, this is in 2 letters, but you have some other generalized quantum cell relations in 3 or 4 letters. Or even, in some sense, quantum cell relations in bigger degrees. But anyway, we have a combinatorics, which is the kind of Lie theory combinatorics. We have some kind of root system. We don't have a bigroup, but we have a bigroupoid, which controls this root system. And for example, it controls at the same time the relations. I use a lot the bigroupoid to find these relations. And you have a PBW basis where you cut the powers by some element related with the degree of this root vector. These are homogeneous elements. This is set to the theta graded as for the small quantum group. Okay. What you can do is to remove from this ideal, essentially you remove almost all the things in the second step. And you obtain a partial quotient, an object between the tensor algebra and the Nicolás algebra. And this is what I call distinguished pre-Nicolás algebra. And the good feature of this guy is that you have a PBW basis given by the same letters. But the difference is that for some subset, which is the subset of Cartan roots, you admit any height. You don't cut this by some order of some root of unity. You put infinite in some of the relations. And in some sense, indeed, if you take the small quantum groups, the pre-Nicolás algebra is the positive part of the big UQ, U psi, really. So this is the pre-Nicolás algebra in that case. So this mimics the quotient taken by the Konchini-Katz processing. This is in the same way. Indeed, what you have is that you can take the powers of the guys in this part, those that you don't quotient, and they define a central Hopf algebra. I put central because essentially for general Q, it is Q central. Q commutes with all the elements. But if you pick up some particular Q, it is central. And what you can, sorry, I forgot to say before this, is that here we have a positive part. But essentially we can go back to the previous construction and construct a big UQ with this in the positive part, a 0 part, which is essentially the algebra, the group algebra of some group that you can choose. And in the negative part, some dual, which is it is similar to the plus part. but with generators f, if you can think quickly. And for this big Hopf algebra, you have this central subalgebra, and you have a Hopf algebra extensions as in the previous way. Because you can do this same construction for small u, which means starting here with the Nichols algebra. So this extension generalizes the extension for the quantum roots and root of unity of the previous slide. Okay, the main point here is that what happens about these Nichols algebras? We can split the list of Heckenberger in three families. The first part is the positive part of small quantum groups. But here, you should admit that this is not only a Lie algebra, if not a contragradient Lie algebra in characteristic 0. There is a second part, which is the analogous of some examples of contragradient Lie algebras in positive characteristic. They have analogous in characteristic 0. This is quite fantastic. For me, when we discovered this, it means that you have a deep relation between the Lie theory and these Nichols algebras that we don't understand completely at the moment. Indeed, we think that we don't understand at the moment because there is a part of this list that we don't control. So we call unidentified type. At the moment, we don't know a way to relate with some Lie theory object. And if you look at all the things in the first line and some in the third line, you can make the following trick. You take your matrix with a lot of root of unity. Then what you can do is to take a matrix over C of Q and to evaluate in a nice root of unity. And you can obtain the matrix with a lot of root of unity as an evaluation of the matrix with over C of Q. Okay, this is at the level of the braiding. What happens at the level of the algebras? What it is fantastic is that you can take U of this matrix Q. Sorry, this should be a different Q. You don't notice here. But essentially, you can take the construction of a Hopf algebra over C of Q, and then you can consider the corresponding Nichols algebra because you have a braiding, so you can construct the Nichols algebra. And when you evaluate, you don't obtain the Nichols algebra, if not the pre-Nichols algebra. So we are in the same way, in the same shape of the Konchini-Katz processi. We have an algebra over C of Q, and we take the evaluation, and we obtain an algebra over Z with a big center. I need a last ingredient for this part. You can do Lustig work in the dual way. You can consider the dual, you should say graded dual, of the pre-Nichols algebra. What happens is that it contains the Nichols algebra, and you have a quotient, as in the Lustig case, which is the positive part of some semi-simple Lie algebra. We started this work with Ferreira Rossi Bertone in 2015, and we are we are going to publish this paper with the whole answer soon. This is what we have. And this Lie algebra will be important for the next step. Let me tell you what is the main theorem of our work. Finally, I reached the main theorem of our work. Essentially, with the previous construction, what we can see is that UQ is a Poisson ZQ order. I recall that ZQ is the subalgebra generated by this power, not the center. So, what we do is to take this evaluation procedure and then to check that it restricts to ZQ. And here we have a very general result, which maybe it is useful for some other context. With the evaluation procedure, you define a Poisson order over the center, as I said. But you can check that if you have a subalgebra, which is stable by some skewed derivations, not usual derivations, then the Poisson structure restricts to the intersection of the kernels of these skewed derivations. And this is the context for our work. So this is, I wanted to stress this point because it could be useful. Once we have the Poisson order, then we can check what is the algebraic group behind this. And we have a solo Poisson group. And moreover, it has a Levi algebra structure, which is the dual of the standard Levi algebra structure of the previous algebra that I defined in the previous slide. So in some sense, we have a strange object, but the structure is not so strange. And as we have a Poisson order, then we can study the representation theory of the big algebra, UQ, starting from the geometry of Q. We applied the previous result about the symplectic course, and then we don't need to describe all the quotients by maximal ideas. We can take a representative for each symplectic core. This is the main point. Because you know that otherwise they are related. They are isomorphic. And, okay, I may add something in words. I didn't want to write this. What happens is that these quotients, AS, these quotients, are Hopf-Galois objects over the initial small quantum group, the corresponding small quantum group. So at the Hopf algebra level, we know the structure of this AS. This is not so strange. This is quite important. Okay, this is the main theorem, and what remains? First, a couple of remarks. What was a surprise for us is that in this way, we have a uniform way to describe the representation theory of quantized enveloping algebras of, for example, contragradient Lie superalgebras. What happened for the Konchini-Kat process is that they use a lot that they have enveloping algebra of this Lie algebra. They use a lot the particular structure of this. In some sense, here we abstract this one, and we don't use the particular structure that we have inside. We try to solve this in a general way, and this was the way in which we thought this at this point. Try to think in a general way to describe Poisson orders for these Hopf algebras. And inside the work, we have, for example, the previous thing that I said about the skew derivations, that we have some other results described in a general way that we applied for our context. This is the content. This remark is about the content of the work. What is the future work? Okay, the Konchini-Kat processor, for example, state a conjecture saying what is the dimension of the irreducible modulus, which it seems that there is a solution, a recent solution about this conjecture. The question is what happens in general. The formula should involve the structure. In that case, this involves the symplectic leaves and also the Weyl group. So here the question is, for example, if the Weyl groupoid is involved in these formulas and what happens in this case. And the second point that we want to obtain is what happens for all the Nichols algebras in the previous classification by Heckenberger. Because I said, for example, for those analogs of contragradient Lie algebras in positive characteristic, we don't have a Poisson structure. Why? Because we can't do this evaluation procedure. So the question is if there is some other way to introduce Poisson order and to find something here. Because the central Hopf subalgebra do exist, but we don't know if we have a Poisson structure. And just to finish, a small example about the Lie superalgebras. What you can take is the analogous of SLM, which is, well, here you take an even and an odd part inside SLMN. In some sense, you take a superspace, and then you take the corresponding matrices with some supertrace equal to 0. I can describe this from the level of the Nichols algebra. Essentially, we need a braiding where we fix a root of unity. Here, Q should be psi. Sorry, I write this example at the end, and I wrote it quite quick. This Q should be psi. And essentially, in the diagonal, we take psi until the position m. Then we take a -1, and then I take the inverse of this root of unity. And for the products Qij, Qji, it doesn't matter so much the individual value of Qij, if not the product. We take the inverse for consecutive vertices in the first half, and Q in the second half, and 1 if the I and j differ in 2 or more. This is what you do. And we can define an analogous linking diagram, and you can see that you have a line as for SLM. This is what you have. In this case, the root system is the same as for AN case. The sum of simple roots from I to j. Then you can define the root vectors, which are the iterated adjoint action in the same order. And the Nij is N alpha ij. This is what I try to mean. It is N in the first half or in the second part, and it is 2 if you take a root passing through the middle. This is the way in which you can think this root. The question is if you pass through the middle or not. What happens at the level of the D superalgebras? It means that you have an even or an odd root. This one corresponds to even roots, and this one corresponds to odd roots. And the corresponding Lie algebra is SLM times SLN. So the algebraic group that we have behind this is SLM times SLN. What happens here is that we have a big algebra with roots which are even or odd. For the pre-Nicolás algebras, we keep the even roots, but the odd roots, you have no solution. They to the square are 0, so in some sense they don't appear. But even I can add the question to the previous slide. As many of these examples come from Lie superalgebras, do you have a relations with Lie supergroups? Because at the beginning, at least we obtain a Lie group, but the question is if you have something else related with these -1s that appear in the middle. So I wanted to express this example to show the relation with Lie superalgebras, and also to put this question. Do you have some superstructure behind this? At the moment, we don't know. Thank you.
Other questions? Other questions?
This is what we are discovering, that you have the same dual version. I mean, I wrote this for the 0 part, VQ, which is the Nicolás algebra inside the dual of the pre-Nicolás algebra, and then you go to the quotient, which is the classic, this guy. I put a Q here because it depends on the Q. Well, you have a whole word. At least for this case, you can obtain by evaluation. But we are discovering that you have this structure for the whole thing. And that's the reason why we're thinking that in a dual way, you have the same. You have the small UQ inside some kind of divided powers. Well, I should write with a different U. And then your quotient to U of the corresponding GQ. And in some sense, you have 2 different kinds of representation theory, because this one, what you try to do is to mimic the Lustig work, to study, to have, in this case, you can think in Huygens-Way categories, not in the other case. Yes, you have the same picture.
More questions?
I have a very basic question about the beginning. You said, when you defined deformed enveloping algebras and the relations at the beginning, you said there's usually a denominator appearing, right? It is E, F minus Fe is equal to K inverse divided by Q minus Q inverse. And you said you can do away with the denominator. How do you actually do this?
You change Fi by a scalar of Fi. This is what you can do. And you keep all the other structure. For the representation theory, it's better to take the quotient by Qi minus Qi inverse, because in that case, you have the Q numbers appearing everywhere. Otherwise, you have to multiply by all the time by these guys.
Yeah. Mm-hmm.
That's the reason to take, in some sense, this quotient. But this way, without any quotient, is the way to construct Dirichlet Ws.
More questions? Thanks a lot.
Thank you.
So there should be coffee downstairs.
Pues estamos aquí, Mardonio Carballo y yo, para convidarlos al Colegio Nacional y también a este museo a un diálogo de experiencias compartidas. Los pueblos originarios, Mardonio, como tú sabes muy bien, consideran que los hombres de cierta edad, las mujeres de cierta edad, son personas de juicio, son personas cargadas de experiencia, y a ti se te ocurrió recoger esto para que dialoguen en distintas disciplinas personas que son decanos de su profesión con los que empiezan esa misma trayectoria de vida.
Sí, la gran maravilla, ¿no? La gran maravilla de tener también jóvenes expertos en temas diversos que de alguna forma importan pues en general al público, ¿no? A la vida, ¿no? Hablar de la vida a través del tiempo, hablar de la experiencia, hablar de la sapiencia también, ¿no? Que da la posibilidad de llegar a ciertas edades ejerciendo ciertas profesiones, ¿no?
Vamos a estar en diálogos los viernes hasta que acabe el año, prácticamente hasta el 13 de diciembre, y vamos a arrancar el próximo viernes 2 con un tema muy importante: identidad, pueblos, política, comunidades originarias de México. Vamos a seguir con el exilio español en México, un decano del exilio español hablando con una descendiente del exilio español. Seguiremos con un tema muy importante: salud, medicina, enfermedad, y así vamos a continuar con algunos de los temas más significativos de nuestro tiempo, contando con expertos ya muy probados, pero también con jóvenes que muy pronto serán expertos.
Sí, y qué maravilla que podamos tener un evento así. Esto es en colaboración con la Dirección General de Culturas Populares de la Secretaría de Cultura y el Colegio Nacional, ¿no, Juan?
Los viernes a las 7 de la noche, ahí en Donceles 104, Centro Histórico, los esperamos en el arranque del ciclo.
Juego, diálogos a través del tiempo.
Pues estamos aquí, Mardonio Carballo y yo, para convidarlos al Colegio Nacional y también a este museo a un diálogo de experiencias compartidas. Los pueblos originarios, Mardonio, como tú sabes muy bien, consideran que los hombres de cierta edad, las mujeres de cierta edad, son personas de juicio, son personas cargadas de experiencia, y a ti se te ocurrió recoger esto para que dialoguen en distintas disciplinas personas que son decanos de su profesión con los que empiezan esa misma trayectoria de vida.
Sí, la gran maravilla, ¿no? La gran maravilla de tener también jóvenes expertos en temas diversos que de alguna forma importan pues en general al público, ¿no? A la vida, ¿no? Hablar de la vida a través del tiempo, hablar de la experiencia, hablar de la sapiencia también, ¿no? Que da la posibilidad de llegar a ciertas edades ejerciendo ciertas profesiones, ¿no?
Vamos a estar en diálogos los viernes hasta que acabe el año, prácticamente hasta el 13 de diciembre, y vamos a arrancar el próximo viernes 2 con un tema muy importante: identidad, pueblos, política, comunidades originarias de México. Vamos a seguir con el exilio español en México, un decano del exilio español hablando con una descendiente del exilio español. Seguiremos con un tema muy importante: salud, medicina, enfermedad, y así vamos a continuar con algunos de los temas más significativos de nuestro tiempo, contando con expertos ya muy probados, pero también con jóvenes que muy pronto serán expertos.
Sí, y qué maravilla que podamos tener un evento así. Esto es en colaboración con la Dirección General de Culturas Populares de la Secretaría de Cultura y el Colegio Nacional, ¿no, Juan?
Los viernes a las 7 de la noche, ahí en Donceles 104, Centro Histórico, los esperamos en el arranque del sitio.
Huehue, diálogos a través del tiempo. La maravilla de tener también jóvenes expertos en temas diversos que de alguna forma importan pues en general al público, ¿no? A la vida, ¿no? Hablar de la vida a través del tiempo, hablar de la experiencia, hablar de la sapiencia también, ¿no? Que da la posibilidad de llegar a ciertas edades ejerciendo ciertas profesiones, ¿no?
Vamos a estar en diálogos los viernes hasta que acabe el año, prácticamente hasta el 13 de diciembre, y vamos a arrancar el próximo viernes 2 con un tema muy importante: identidad, pueblos, política, comunidades originarias de México. Vamos a seguir con el exilio español en México, un decano del exilio español hablando con una descendiente del exilio español. Seguiremos con un tema muy importante: salud, medicina, enfermedad, y así vamos a continuar con algunos de los temas más significativos de nuestro tiempo, contando con expertos ya muy probados, pero también con jóvenes que muy pronto serán expertos.
Sí, y qué maravilla que podamos tener un evento así. Esto es en colaboración con la Dirección General de Culturas Populares de la Secretaría de Cultura y el Colegio Nacional, ¿no, Juan?
Los viernes a las 7 de la noche, ahí en Donceles 104, Centro Histórico, los esperamos en el arranque del sitio.
Huehue, diálogos a través del tiempo.
Pues estamos aquí, Mardonio Carballo y yo, para convidarlos al Colegio Nacional y también a este museo a un diálogo de experiencias compartidas. Los pueblos originarios, Mardonio, como tú sabes muy bien, consideran que los hombres de cierta edad, las mujeres de cierta edad, son personas de juicio, son personas cargadas de experiencia, y a ti se te ocurrió recoger esto para que dialoguen en distintas disciplinas personas que son decanos de su profesión con los que empiezan esa misma trayectoria de vida.
Sí, la gran maravilla, ¿no? La gran maravilla de tener también jóvenes expertos en temas diversos que de alguna forma importan pues en general al público.
So it is a great pleasure to introduce Professor Claudia Polini. She's in the University of Notre Dame. He got his PhD in 1995. And he's a fellow of the American Mathematical Society. And he, because of his contribution to commutative algebra and for service to the community. And she's going to talk about the degree of vector fields.
Okay, I would like first to thank very much the organizers to have given me the opportunity to give this talk. I would like to thank my brother, Rafael Villarreal, to have introduced me and to give me the opportunity to come back to Mexico City. It's always a pleasure to be in Mexico. It's a fantastic and wonderful country. So I hope you'll enjoy my talk. I'm going to talk about the degree of vector fields, and I will talk about it mostly from the algebraic point of view. So let's start considering a polynomial vector field in C2. And to think about a polynomial vector fields, we just need to take two polynomials, P and Q, with coefficient in the complex number, and we assume that P and Q are relatively prime. We make this assumption so that the polynomial vector fields is defined almost everywhere. Now, obviously, being a polynomial vector fields to every point you have a vector associated to it. Now we want to think about these vector fields actually also as an element on the module of derivation of the polynomial ring, Cxy. And remember, the module of derivation is a free module, and as a basis, the partial derivative with respect to x and the partial derivative with respect to y. Now, we say, we say that such polynomial vector field as a rational first integral or is algebraically integrable if there exists a rational function such that the differential equation associated to the vector field as a solution, a rational solution. So eta f is equal to 0 for some f which is a rational function. And obviously we are very interested in finding solution of differential equations. And connected to this definition, there is the definition of when an irreducible algebraic curve is left invariant by the vector field. So an irreducible algebraic curve C is defined by a polynomial f, a reducible polynomial f, and we say that the algebraic curve is left invariant by the vector field if for every point non-singular in the curve, when you take the vector that you obtain evaluating P and Q at the point P, this vector is tangent to the curve at the point. So what you want is that the curve follows the flow of the vector field. And then you say that the curve is left invariant by the vector field. So let's see this definition in an equivalent way. So this is the definition I just gave before. And equivalently, if you want that, a vector is tangent to your curve, you can describe this also in terms of the gradient. So this just tells us that the gradient is at the point is perpendicular to the vector field. But now if we look at this equation, this is the same, remember the equation of the vector field eta, this is the same as saying that f is a solution of the differential equation given by eta, but only for the point of the curve. So again, we have a solution, but we don't have a solution globally. We just have a solution on the curve C, okay? So, but now think about it this way. The eta f is 0 on the curve. However, the points of the curve are given exactly by the equation f equals 0. And by the f is irreducible. So by the Hilbert-Nustellenses, the fact that eta f is 0 means that eta f has to be a multiple of f. So we get that eta f is just h times f for a polynomial h. And now think about this in terms of the derivation again. Eta is a derivation defined on the polynomial ring, but it sends the ideal generated by f to the ideal generated by f. So eta induces a derivation on the coordinate ring of the curve, on the factor ring cxy modulo the ideal generated by f. So now if we summarize this, this tells us that a vector field eta leaves invariant a curve exactly if and only if, when we think about eta as a derivation in the polynomial ring, it induces a derivation on the coordinate ring of the curve. And now, how is this connected in any way to the fact that the eta, thought as a differential equation, has a rational solution? It is, and it was pointed out first by Darboux in 1878, and then done in much more generality and more modern term 100 years later by Joannalou. And they prove that eta has a rational first integral if and only if eta leaves invariant infinitely many curves. Obviously, if we say it in this term, this does not help us discover when we have a rational first integral. However, much more interesting, they prove that this is infinite if and only if eta leaves invariant a finite number of curves, and actually we know what this finite number is, and it can be expressed in terms of the degree of the vector field, where the degree of the vector field is the maximum of the degree of P and Q that appears when we describe the vector field. So it says eta leaves infinitely many curve invariant if and only if eta leaves at least 2 plus 1 plus the degree of eta choose 2 curves invariant. So the question now is, when does eta as a rational first integral? And to answer this question, we should be able to describe all or as many as possible curves that eta leaves invariant. How could we describe such curves? How could we find them? But Poincaré pointed out that one way to find them was if we could bound their degree. Because if we can say that the degree of such curve, which are just given by f, a polynomial, if the degree of the polynomial is bounded by a certain number, then you have to only look in a finite dimensional vector space, the finite dimensional vector space that you get up to that degree. So is a finite quest. The problem is that in general, you cannot bound the degree of f just in terms of the bound of the degree of the vector field. That's not possible. This is already present. This example that I present here is already present in work of Carnisser. You can see that if you fix, for example, m, an integer, which is at least 2, and you consider the vector field given by the 2 polynomial mx and y, so this is a vector field of degree 1, okay? Then the irreducible curve that is given by f, the polynomial, for example, ym minus x, this is a curve of degree m, okay? This curve, C, is left invariant by eta. If you want to just take a piece of paper, you do the computation, you see immediately when you take the partial derivative, this is a multiple of f. So this is indeed the case, but the degree of f, as you see, grows with m, while the degree of the vector field is always 1. So the degree of f cannot be bounded by the degree of the vector field. And even though in this case we do have a rational first integral, each of these eta has a rational first integral that you can obtain just by, even by the curve is ym over x, okay? So even in that case, we cannot bound it just by the degree of the vector fields. So the problem now becomes of the taller magnitude, and it becomes how can we relate the invariance of the curves to the invariance of the vector fields. And we cannot just consider degrees. We must consider other kind of invariance, local and global. So actually what we want to do now, we want to work not just on affine space, but we want to work on projective space. And we don't just want to work on the complex number, but we want to work on a field K that we assume, though, algebraically closed. And so we are going to consider vector fields in Pn over K, and we'll consider not just curves, but reduced subschemes of Pn, and that are left invariant by such vector fields. And now the task becomes to, as I said, make a relation between the invariance of eta and the invariance of x. And I will show which kind of invariance we consider in the next. So first of all, let me mention the name of some people that have played a role on this game and that have worked hard to answer these questions. This is an incomplete list, as you noticed, and if you are aware of the fields, that most of them, actually all of them, are not commutative algebraists, so we came from a little bit of a different perspective. The people on this list, the one that influenced us the most, were definitely the work of Esteves and Esteves-Kleiman, of Linz-Neto and Soares and Duplessis and Wall. These were the people that influenced most our work. And let me tell you that the work that I'm reporting today is joint work with Marshall Den, Hamid Hassanzadeh, and Aaron Simis and Bernd Ulrich. And two of them are in South America, in Brazil. Let me start actually giving the algebraic formulation, because as I said, we see this from the algebraic point of view. So I assume now, as I said before, that K is a field which is algebraically closed, but for the sake of this talk, I will assume that as characteristic 0. Really, this is not important. It's just to make the talk simpler. And we consider a polynomial ring in n+1 variable over K. I'll call it big X, the variable. And then again, I consider a vector field. But now I want to give you the definition of a vector field on projective space. So to start with the definition of a vector field on projective space, which I'll call eta, I have to start with a vector field on a affine space, just like I did before. So I'll start with Xi, which is a vector field OAN+1, and is defined, just like before, by polynomials. Only that this time, because I want to get a vector field on projective space, I have to assume that my polynomials, which I call A0, A1, An, are actually forms, homogeneous, and they all have the same degree. And I'll call this degree M, because I want to find a vector field of degree M. And as before, this will be very useful, I consider these vector fields as an element, as a derivation over the polynomial ring. Okay? And as a derivation, be careful, this has degree 1 less, because the partial derivative has degree -1. So as a derivation, this will be important later, as degree M-1. So now we want to say what it is a vector field on projective space. How do we get it out of Xi? Okay, Xi induces vector fields on the affine charts of Pn. Now, the way to get it, I mean, this maybe looks complicated, but it's actually not difficult. You have to do the change of variable and pass from the xi to the xi over xj, and then you have to do the partial derivative with respect to the new variable, and if you write it, you get this kind of coefficient. And now, together, all these vector fields on the affine charts give me the vector fields on projective space. And this is what the vector fields on projective space is. Now, the vector fields on projective space obviously will have a singular locus. And the singular locus will be given when this guy are all 0. Okay? So the thing on top, xjii minus xiij are all 0, then we get a point in the singular locus. So it's given as a subset of Pn by the 2 by 2 minor of that matrix, where the first row is the variables and the second row is given by the polynomial AI that define the vector fields in a fine space. Okay? Now again, I want to see what it means that this eta leaves a variety of a scheme invariant. So before doing that, let me tell you what it means. How do I think about the vector in the vector fields? So if I have if I consider all projective space and I take a point in projective space which is not in the singular locus, what's happened? It happens that I get actually, when I evaluate the AI at P, I get a point which is different from the point P. So it's like a rational map. The eta gives me a rational map from projective space to the Grassmannian of lines. To every point in projective space, you just associate the direction, the line through P and AP, which is well defined because AP is different from P, because I'm not in the singular locus. So this gives me exactly the direction, the flow of the vector field. This map, which we call capital Phi. And now I want to see what it means that eta leaves my X invariant. So let's consider a subvariety. So I consider this guy, the coordinate ring will be a domain, the subvariety in Pn, and let's say that the coordinate ring is defined by an ideal, which I call homogeneous, which I'll call I of X. And now be careful, I write this algebra, this is the coordinate ring with small x's. These are not variable, they are the images of the x, the big x's in R. And then I denote with M the homogeneous maximal ideal of R. So that's M. When I have to define this, what does it mean that the vector fields leaves X invariant? I need remember, I want to do this in terms of derivation. So I need a particular derivation, which is the one that we always think of it, which is the Euler derivation. The Euler derivation is the one that is defined by the x's. Okay, with polynomial, the coefficient are the x's. And now, what does it mean? So eta, remember, is the vector fields on Pn induced by Xi, and Xi, I think of it as a derivation on the polynomial ring. All right? And now I want to think what it means that eta leaves my X invariant. Before, when I thought about the curve, it meant that Xi induced a derivation on the coordinate ring of the curve. I want something similar. And why is something similar true? But we have what we have. We have that, again, as I said before, we want the variety to follow the flow of the vector field. So we want that for every P in X, which is not like before, it should be a point that is smooth on the variety. So I have to take off the singular locus of the variety. And I also should take off the singular locus of the vector field. So I want a P which is in X and not in the singular locus. I want for each of these P that phi P, which is exactly the vector I get from the vector field. Phi, remember, is the map I just defined before from projective space to the Grassmannian of line, should be tangent for every P to the variety at the point P. Okay, should be in the tangent space. And now, as before, I can describe this in terms of derivation. This tells me that Xi, this is if and only if Xi induces a derivation on R. R is the coordinate ring of the variety. This requires some work. I didn't put it. I didn't want to put all the proof of the details, but it's not difficult to see. But now be careful, because we want this eta to leave X invariant, but this to have a meaning. And to have a meaning, since we are taking the point X of X which are not in the singular locus of eta, we would like to consider the vector fields such that the singular locus does not contain all variety. Otherwise, there are no points to consider. So we want to not only that eta leaves X invariant, but we also want that the singular locus of eta does not contain X. So for this reason, Xi should not just induce a non-zero element. in the derivation of R, but it should induce a non-zero element in the derivation of R modulo M inverse epsilon. And what is this M inverse epsilon? M inverse is just a fractional ideal. So this is the multiple of epsilon with this fractional ideal, which is the element in the fraction fields that sends the maximal ideal M into R. Okay? Again, this requires a proof, but it's not difficult to show, and these are exactly the element we consider. So I want to explain why is this important. So let me first summarize it, and then I tell you why it's important, this point of view. So what we just proved, or at least I gave you an idea of what's true, I didn't really prove it for you, is that I have a vector fields in a affine space, and this vector fields in affine space induces a vector fields in projective space, and this vector fields in projective space satisfy first the fact that the singular locus of this vector field does not contain my variety, and second of all, it satisfies the property that this vector field leaves the variety invariant. And this is true if and only if this C, the vector fields in affine space, which I think of a derivation in the polynomial ring, introduce a derivation, introduce a non-zero derivation in their R modulo M inverse epsilon. Why is this important? Because somehow what we did is this. We did the opposite, we took the opposite view with respect to Poincaré problem. Instead to consider fixed vector fields and try to describe all the curves that the vector fields leave invariant, we did the opposite way and we said, let's fix X, let's fix my variety, and let's see if we can describe all the vector fields in projective space that leaves this variety invariant. And the advantage of taking this point of view is that commutative algebra gives you a beautiful way to encode in a single module all the vector fields that leave this X invariant. One single module tells you all the vector fields. Every element of that module leaves me my X invariant. Any vector fields that leave my X invariant has to live in that module. So I have a way to concretely think about all the vector fields. And now I can answer the question. Because the question was, you can say, you cannot answer the question because the question before was, fix the vector fields, gives me all the curves that are left invariant. But I can just do the opposite perspective. I can fix X and give you all the eta that leaves X invariant. And if I want to bound the degree, think about it. We wanted to bound from below. We wanted to say the degree of the curve should be less than equal than something if it's left invariant. Then you can say the degree of the vector field should be bigger than equal than something if it leaves the curve invariant. It's the same thing. So what we just want, lower bounds on the, what we want to bound the degree of this module from below, and we'll answer the question. If we can bound it for above, we'll even get a sharp answer to the question. But we just want to bound this module from below. And why do I call the initial degree of this module? Because the initial degree is just the element, the degree of the first non-zero element in that module. That's what I want to find, okay? And that will really tell me answer the question completely. Notice that so the smallest degree of such eta, I have a shift of 1 because I told you when I think about it as derivation, they have degree just 1 less than the vector fields, okay? And that's why is just 1 less. So our problem is just, it becomes to bound the initial degree of this module from below. And that's what I'm going to do for the rest of this talk, is just trying to find bounds for that module. And then at the end, I'll try to show you, wow, they are sharp, in which case they're sharp. Let me first give you a sample theorem that gives you an idea of actually before the sample theorem, let me show you which invariants come to play a role on this. So, and before doing that, let me tell you how you can think about this module of derivation if you are not used to it. So, the module of derivation, obviously, if R was a polynomial ring, we know it's a free module, and the basis is given by the partial derivative. So it's all done. But if R is not a free module, it's not a polynomial ring, like in this case is a quotient of a polynomial ring, how do we think of the derivation? But it's the dual of the module of differential. And the module of differential is described by the Jacobian matrix. So we start with a variety of dimension D, and we consider the ideal defined by the variety. Let's say that the ideal is generated by forms, F1, Fs, homogeneous as forms. And then we consider the Jacobian matrix first, so the partial derivative of the F, first in the polynomial ring S, and then we consider the images into R. And that's why I write the partial derivative with respect to the small x's. This is really just the image of the Jacobian matrix into R. And the dual of such matrix would define my module of differential. The module of differential is just the co-kernel of the dual of that matrix. But the derivation are the dual of the module of differential, so they are given by the kernel of that matrix. And the kernel are much harder to describe than co-kernels. We know that, so this will be much harder to give. So this is just the kernel of that matrix, so you start from a free module given by the partial derivative, and it goes into the matrix phi is a S times n plus 1 matrix, and that's how we think of it. We think about the modular derivation as this kernel. Now, the Jacobian matrix also gives us another important ingredient, which is the Jacobian ideal, which defines the singular locus of your x, which we know is very important because we have to take the point x that are the points that are in the variety and are not in the singular locus. So what is the Jacobian ideal? The Jacobian ideal is generated by the codimension size minors of the Jacobian matrix. And as I said, the singular locus of the variety is just V of the Jacobian ideal. So these are obviously going to be, this is going to give us, the Jacobian ideal is going to give us the local invariant, they're going to play a role, and now we want to look at the global invariants. So which are the invariants that we're going to play with? We said the degree is not enough, okay? So to bound this initial degree of the module we are interested in, we cannot just consider the degree of the variety. We should consider something more. So let's see what we consider. So let me call A just a factoring of a polynomial ring by an homogeneous ideal that I call J. T is just a polynomial ring in n variable. And let's call D the Krull dimension of this factor ring. Then we say that the factoring is Cohen-Macaulay if the projected dimension of A thought as a T module, notice that T is a regular ring, so has global dimension finite. So if we take A, which is a finite module, it has finite projected dimension. And now the projected dimension is the smallest possible, is the codimension of the ring, which is n minus t. And now we consider the canonical module of A, which is the first non-vanishing x, which is the x at the codimension of A against T twisted by minus n. This is also called the dualizing module, and if A happens to be Macaulay, is the only non-vanishing x, the only one. And it's called the dualizing module because it gives a duality. If you do Ohm in omega A, it gives a duality on the category of maxima Macaulay A modules. Now, the invariant that we are going to use comes from this canonical module. In fact, we can consider the initial degree of this canonical module, the first place where it starts, and take minus this initial degree. And this we call the A invariant of A, and this is the global invariant that is going to come in our bounds. Now, if A is Goresten, not just Macaulay, So what does it mean that A is Goras? It means that it's Comecoli, and the canonical module is the simplest possible, is isomorphic to your ring with a shift which is going to give by the A invariant, because the canonical module starts at minus A. And now let's go back to our situation where R is the coordinate ring, homogeneous coordinate ring of a subvariety X, okay, in Pn, and this is the dimension of X. How do we relate this invariant, which is called the A, the one I just talked, this A invariant, to the global invariants that most probably you are more used to? So the first invariant that usually we know, and the one I told you is not enough, is the degree of the variety, which is actually the same as the multiplicity of the coordinate ring, which is just the number of points that you obtain when you take the variety and you cut it down to dimension 0 by general hyperplane sections. And this is this number of points. Since we consider we are in characteristic 0, this is just reduced points. We just get points, remember. So we just get points, and we count the number of points. And now, if X happened to be a plane curve, then the degree is just the degree of the form, F. That's the kind of bounds we asked at the beginning when we looked at Poincaré problem. The next global invariant that you may be more used to, which I'll not really define, is the regularity of X. The regularity of X is the regularity of a coordinate ring plus 1, and I won't define it, but you can read it off of the projected resolution, from the shift of the projected resolution. It's also given by vanishing of local cohomology. And how is this regularity that you may be more connected to the A invariant? It's connected to the A invariant in general. First of all, let me tell you that for a plane curve, the regularity is again just a degree, okay? And now, in general, the A invariant, that is as I said, the invariant we will actually focus on, is always less than equal than the regularity of the variety minus the dimension minus 2. And this bound is actually an equality if R is Comecoli, or if you want, X is arithmetically Comecoli. So you could, when you have Comecoliness, the bounds that I'm going to write now, you can read it in terms of regularity. And if you have plane curve, you can just read them in terms of the degree of the curve. So let me first give you the sample theorem. This is just a special case of the kind of theorem I'm going to show you. It's not the only result we have. We have many, many more. But this was maybe the easiest one to describe. So let's take a curve now in projective space, and let's assume that as only ordinary nodes as singularity, then the initial degree of the module we are interested in, remember, this is really the collection of all the vector fields that leaves my curve invariant. The initial degree of this module is bigger than equal than A invariant of R plus 1. And equality holds if in addition we assume that X is arithmetically Gorestan. Then we actually get equality. This was known already if the curve X is planar by the work of Serval and Snato in 91, and then it was also known by work of Campillo, Carnicer, and Garcia de la Fuente, if it's a complete intersection, and then by work of Eduardo Esteves, if the curve is arithmetically Comecoli. Now, for the bound that I put up there, we need very much the information about the singularity, and instead to have the other bound, a less than equal, that we don't need any information of the singularity. We'll see it at the end. We just need information about the Gorestan property. So let me describe how we get to this sample theorem, what is a corollary of. So let me start with general projection. The method of general projection was inspired to us very much by the work of Esteves. So you start with X okay? It's your variety in Pn, and you want to project, but you remember the dimension of X is D. I want to project, take a general projection, and I want this map to be finite and birational. So I get to another variety which has the same dimension as X, dimension D. So this variety will be in PD plus 1, and will just be described by a simple equation, one equation. So it will be an hypersurface, will be a complete intersection, so it will always become Macaulay, and actually Gorestan. And then what we want to bound the initial degree of this module of derivation, this factor of the module of derivation for X. But we want to project to Y and bound it for hypersurface and then lift it back. So we have to know how these two initial degrees are related. And we hope that the way they are related is connected with our global invariance. And in fact, what we can prove is the following. So this is the algebraic formulation. A corresponds to the coordinate ring of Y. R is the coordinate ring of X. Remember, because Y is an hypersurface, A is always Gorestan, is actually even a complete intersection. And the map, the projection was finite birational, so you have a finite birational inclusion of rings, of standard graded K-domains. They were varieties, so this is an inclusion of standard graded K-domains. And then what we get is that the initial degree of the module that corresponds to X, this is the module of derivation of R, module M inverse epsilon, minus the initial degree of the module that corresponds to Y, this is the derivation of A over A times the Euler of A, is bounded below and above by the difference of the A invariance. Exactly the global invariance I want to consider. Notice that in the module corresponding to Y, I don't have M inverse, I just have A. This is because A is Macaulay, so M inverse of A is simply A itself. So now I'll try to indicate a proof. Let me tell you that Esteves had a similar result in the case in which X was assumed to be arithmetically Macaulay. Our proof is completely different. He obviously expressed it in terms of regularity because I told you the invariant and the regularity are connected, very much connected. In the case, you can pass from one to another. In the case in which X is arithmetically Macaulay. But the proof is completely different. I want to indicate our proof because it's very simple. So first of all, we consider the conductor of R into A. What is the conductor? I'll denote it with F, and it's the element in A that sends the ring R into A. But because the map is birational, you can think of it as the A homomorphism of R into A. Every A homomorphism is just given by multiplication by an element of A that sends R into A. And now this homomorphism ring, I can write it doing a little trick. I shift the A inside, and then I have to undo the shift. But this is very useful because if I shift it using the A invariance of A, I can think of A shifted of A as the canonical module, as the dualizing module of A, because A is Gorestan. Here I use the Gorestan property. And doing that, this homomorphism ring of R into the canonical module is again a dualizing module for R. Even though R is not Macaulay, it's still a canonical module. And this shifted by minus A. This allows me to compute the initial degree of the conductor. What's going to be the initial degree of the conductor? Then we can compute it now in terms of the initial degree of omega R. So it's going to be A, because it's shifted by minus A, plus the initial degree of omega R. But the initial degree of omega R was minus the A invariant of R. So we get that the initial degree of the conductor is the difference of the two A invariants of the two coordinate rings. And now what does the conductor has to do anything with our problem? But first of all, remember we were interested in the module of derivation of R and A. And we can embed both modules in a common module. So how do we embed them? But the embedding of the module of derivation of A into this larger module is very easy. You just compose any derivation with embedding of A into R. And the embedding of the derivation of R into the derivation of A and R is also very easy. You just restrict a derivation to A. Now the point is that these two embedding, they still remain embeddings after I go modulo this fractional ideal that I described before. So, and this is because this module are torsion-free. So I get two embedding, which I'll call phi and psi. And you can see the top left guy is the guy I'm interested with which are this vector fields that leaves my curve invariance. They are the particular one that they don't contain the singular locus, they are non-zero, and that the other module as well is the one relative to the y, and one is the one x. So these are the two modules I'm interested in. They both appear there. So what does the conductor have to do anything with it? But the conductor sends R into A, so he kills both of these two co-kernels. What the conductor does is sends every element of the top, the guy up here, into this and into this. So if you multiply an element of the conductor, it sends R into A, so it sends back every element here to here. And it also sends every element of here to here. So what we get that the co-kernels are killed, but if the co-kernels are killed, this also means that if I take an element in the image of phi here, it's inside here. And if I multiply by the conductor, it goes to finish here. So it goes to finish in the image of psi. So what I just said is that the conductor sends the image of phi inside the image of psi. And the same is true for the other. The conductor sends the image of psi in the image of phi. But then, since I have domains, remember, first of all, that since these are two embedding, the modules are isomorphic to the image. Second, because I'm in a domain, I can read the initial degree is just additive, and then I have that the initial degree of the conductor plus the initial degree of the image of phi is bigger V equal than the initial degree of the image of psi. And this is true because the conductor times the image of phi is a submodule of the image of psi. So every element in it has the initial degree at least as big as the initial degree of the image of psi. So I get this equality, which immediately give up my theorem, because the image of phi is exactly the module I'm interested in for x, and the image of psi is the module that I'm interested in for y. And the initial degree of the conductor, as I said before, is the difference of the A invariants. So this is the only proof I want to do, so don't worry, I'm not trying to prove anything else. I just want to put things together now. So doing this general projection allows us to go in the case of hypersurface. Then we still have to do the work for hypersurfaces. And so now we do lower bounds for the initial degree of this module for hypersurfaces. So we take an hypersurface of degree delta with at most isolated singularity, and then we can prove that this initial degree is bounded by the minimum between delta minus 2, which is just nothing else than the A invariance plus 1, which is exactly the bound I told you, and then n times delta minus 2, the A invariance of the ring R defined by the Jacobian, R modulo the Jacobian. It's clear that the Jacobian has to play a role because the singularity play a role, minus 2. And this kind of bounds was already, first of all, let me tell you, we prove this kind of bounds thinking about this module of derivation as the kernel of the Jacobian matrix, okay? And then we use linkage. I will not give the proof. I'll just say that this was first proved by Esteves and Kleiman for n equal 2 for plane curves. And then for plane curves, you get actually a better bound, and this time the bound is in terms of the number of singular points in X, the singular points of X, and in terms of what's called the Helmholtz, of R over the Jacobian. I think the first person that called this invariant L mult is Vasconcelos, and I'm going to try to describe it to you in the next slides. And this L multo is always less than equal than the multiplicity. So you can also express it in terms of the multiplicity of the ring defined by the Jacobian. So I'm going to describe now this bound. Okay? So this is for plane curve. So instead to give you, I won't give you a proof, I'll just tell you what these invariants are. So we consider this ring, which is defined by the Jacobian ideal. Okay, I'll call it A, and we consider the singular points of my varieties. These are exactly the minimal prime of the Jacobian ideal. We call it P1, Pt. And then we look at the multiplicity of this ring, and the multiplicity is, by the associativity formula, just the sum of the co-length of the Jacobian is the length of A localized at Pi. Okay? And this is the same as in this case, because we have a complete intersection with isolated singularity, is the sum of the Turina numbers of R localized at Pi. And the Turina numbers are the embedded dimension of the base of the versal deformation, which are that deformation that give us all the other deformation by base change. And the Turina number already appears in this count of bounds in the literature. And now we, as I said, talk about L mult. So what is the L mult? But you get the L mult from the multiplicity in a certain sense. You take the associativity formula for multiplicity, and you substitute the length of A over localized at Pi with the Levy length of A localized at Pi. And the Levy length is the smallest power of the maximal ideal that is 0. Okay, so it's always less than equal than the length. And this is the kind of, invariance that we use. Now notice that this difference between the number of singular points and the L mult is 0 if and only if the singularity are ordinary nodes, because every ordinary nodes count exactly as L mult 1. And remember, the L mult is a local invariance. You can just compute it. You compute it locally at every point. So every singular point, which is an ordinary node, count as 1 in the number of singular points and counts 1 in the L mult. So they erase with each other. Now, this bounds is good, but unfortunately is not as tight. It's tight in the case, as I will show later, but it's usually not tight. But we have much better bounds that I cannot describe here for curves that are in terms of the genus. And actually they're a little bit strange because they involve square roots. And the bounds that we have that are actually, they are generalization of work of Duplessis and Wolz and Esteves and Kleiman. They are actually sharp in the case of genus 0. And in that case of when we have rational curves, we are able even to describe, in the plane at least, we are able to describe not only the generators and their degrees, but even give resolution of this module. So we are able to do much more. But I cannot talk about this now. Now let's put everything together to give you the sample theorem. So this is the theorem I put practically up before. You have a curve with only plane singularity. Then the module we are interested in has initial degree bigger than equal with A invariant plus 1 plus the number of singular points minus the L mult of R over the Jacobian. So to prove it, we first do a general projection. We go to the case of an hypersurface. In this case, an hypersurface is a plane curve because the dimension of x is 2. So we go to the case of a plane curve. Dimension of x is 1. So we go to the case of plane curve. And now, by our theorem on general projection, we know that the initial degree of the module we are interested in is bounded by the difference of the invariant plus the initial degree for the coordinate ring of y of the plane curve. But for a plane curve, we proved the theorem. It was bounded by the A invariant of A plus 1, because it was the degree, and plus the number of singular points of y minus the L mult of A over the Jacobian of A. Now the problem is how to finish the theorem. We should be able to connect that difference in blue with the difference for x. How are they connected? We should show that they are the same. Why is this true? You're doing a general projection. How are the singularity changing? But remember that our x had only plane singularity. So for every singular point of x, what happened is a minimal prime of the Jacobian. If you localize the coordinate ring at P of x, you got the same that if you take the coordinate ring of y, which is A, and you localize it to the contraction of P. So this shows that the equality works for that point. And now for the other, are there any other singular points that you create when you project? Yes, you could create more singularity, but the only singularity you create are ordinary nodes. And for ordinary nodes, we already showed before, we already said before, this difference is 0. So nothing changes. So now we obtain immediately, as a corollary, our sample theorem. And our sample theorem, if you remember, is a corollary because we have a curve with only ordinary nodes, a singularity, so this difference is 0, so it disappears completely, and we just get that the module we're interested in is bounded by the A invariance plus 1. So now I have 5 minutes left, 6 minutes left, and I'm ready to prove why is this sharp in the Goresten case. And it's really very easy, so I'll give you actually a proof of it. But first, let me state what happened. In that case, for showing, these upper bounds, I don't need to assume anything about the singularity, but I need to assume the Goresten property for the coordinate ring. So we have x, which is an arithmetically Goresten curve, so the coordinate ring is Goresten. And then the initial degree of the modulo derivation, modulo R epsilon, just have to take the ideal now generated by epsilon because it's Comecoli. This is less than equal than the A invariant plus 1. And the quality holds if x has only ordinary nodes, as we saw before. Now, be careful because this less than equal cannot hold in general unless you don't have this Goresten property. You need to have even other invariants to bound, to write these upper bounds in that case, if it's not Goresten. So it can fail even if the curve is smooth, okay? So you really need some property about the coordinate ring. Now, I indicate a proof of this when I go to the higher dimension, which is actually work with Ulrich and Claudia Miller. So let me talk about the higher dimension. So x is an arithmetically Goresten variety of dimension d, positive in Pn. Again, I denote with A the A invariant, and with omega, the modulo of differentials. Now, if you consider there are linear maps that you can obtain if you are in the exterior algebra, and you consider the d exterior power of the modulo differential times omega, and you go with exterior multiplication to the d plus 1 exterior power of omega, and then you follow this natural map with the canonical map, which is called the canonical class, which goes to the canonical module of R, but actually a special canonical module is the module of differential forms, the regular differential forms. So it's a special copy of the canonical module. Remember that we assume that our x is arithmetically Goresten, so our coordinate ring is Goresten, so the canonical module is isomorphic to R, shifted by the A invariant. But now, when we obtain a map here, we obtain a map, this composition gives us a map from the d exterior power of omega to the R homomorphism of the modulo of differential into R shifted of A. But remember that if you take the shift out, you get the homomorphism of the modulo differential into R, but this is just a dual of the modulo differentials, and that's the derivation. that is the derivation module that we're interested in. So this is a map between the d exterior power of omega to the module of derivation shifted of A. And so it induces a non-zero map from the exterior power of module of differential shifted of minus A to not just the module of derivation, but even the epimorphic image of the module of derivation modulo R epsilon. So now the beautiful thing of this is that if this module on the left, we know exactly the degree of the generator. This is generated all in degree D plus A. And since this is a non-zero map, this guy, their image is non-zero here. So there will be an element of degree D plus A here. So this shows me that the initial degree of this is at least D plus A. At most, D plus A is bigger than equal than D plus A. There is at least somebody of degree D plus A. So this shows that the initial degree is less than equal than D plus A, which is exactly what I wanted to prove before. So it gives me the upper bound that I was looking for. And it gives me the upper bound in a general situation, even for higher varieties. Now, we can prove more in special, very special cases. We can show that this map that I just described how it comes up is actually surjective. And because this map is surjective and we understand this very well and all its generator, then we know exactly where this module is generated. So we don't only know the initial degree, but we know all the generator. And they are all in degree D plus A. And this is, for example, if X is a smooth complete intersection or if X is a smooth arithmetically Gorestan surface in P5. In general, if it's Gorestan and unobstructed. And in this case, we can actually do more. We can even resolve it, and we know exactly where the generator comes from. They come from the Buxbaum rim. But I would like to say that there was some case treated by Soares earlier, and this was the case of smooth complete intersection in 2000, but with the method were completely different from ours. I would like to thank you very much.
Okay, do you have any questions or comments? Okay. Wait.
Oh, okay. All right, so very pleased with the work. I did work on that before, and you certainly found, the right invariants there, and it's very beautiful. But let me ask you, about the theorem on general projections. For that, you don't need the projection to be general, right? If I understood the hypothesis correctly.
No, I don't need it to be general, no.
Right,
no.
so in principle, you could start with a very singular hypersurface and view it as a projection of something which is not so singular. Could that help?
Yeah, I suppose. But remember, you want to, you have you want information about the singular points. You definitely want to keep the information about the singular points.
So something has to give, right? Because the singular points, the amount of them, the number of them, have a lot of importance in the minimal degree, right?
Yes, yes.
Right? But if you go to something which is not so singular above, then I don't know what changes there.
When you project them, though,
right? Yeah.
You think you're going to get rid of them? I don't think you get rid of them.
No, I just wondering what would happen there.
Yes. Yeah, no, you don't get rid of them. So you want to keep the information because you want to go down and bound it, and then you can lift it up and have the same kind of invariants that show up. So.
Okay.
Yeah.
Okay. Well, food for thought. Thanks.
Okay. Are there any more questions?
Thank you, Claudia. Just one question. Suppose that we are interested in the same problem, but now for vector fields on some projective variety instead of Pn. And then again, you want to consider the same problem.
Okay.
So what difficulty do you expect, and what should go through in this case?
I don't know. I never thought about it, actually. I never looked at it. But So I don't know. I don't really know an answer. So you just want to, so consider them just on any projective. Yeah, define, I don't know.
Okay.
It's an interesting question, but I don't know.
Okay, any more questions? I have one, okay. Okay. In section 4.
Yes?
I wonder if the section 4, there is a very nice 2 bounds, right?
Where the section 4? No. The bounds in terms del mult.
Well, actually, my question is more or less right there.
So when it appears the bound in term el mult, this one.
Before. No,
before.
Before.
Okay.
Right there, yes.
Okay.
No, I just wonder if how good are these bounds, or how tight they are.
But this, so you're asking, I think, you could have room definitely between this module up and the module down. You could have room definitely between the two. Yes. Yeah. And I think even, in the cases that we computed where we know exactly where this is generated, when you get to rational things, we know exactly, So there are definitely space. Yeah.
Claudia, welcome to Mexico.
Thank you.
One question out of this. Where you learn English?
I live in the United States.
Thank you.
Okay, so, thanks, Claudia. So let's thank the speaker again.